Okay, this is one of the toughest questions I've seen involving impulse and momentum. There's a few concepts in there. It also embeds quite heavily into a lot of dynamics going on. So a pile driver mass 1,000 kilograms drives a pile of mass 200. Part of it is the concept. Now a pile driver is a big weight, so this thing here is effectively a big weight that's being pushed down. And the version they're on about here is dropping from a stationary point 10 meters onto the pile. The pile is a rod or a stake or something you're trying to drive into the ground. So we've got the pile and we've got the driver. So draw a quick diagram. Pile driver and pile. The driver drops 10 meters. At the end it's going to be moving in that direction. We're saying it starts at a velocity of 0. So yeah, don't even have to actually give it a direction really, but 0 meters per second. We're going to assume it's not being forced, it's just being driven down using a weight and then falling under gravity. So the acceleration is due to gravity. At the end, we need to know the v, the speed at the end. By modelling as particles, well, the concept of these as particles, oh sorry, I've missed off the masses, but the concept of these as particles is talking about there's no air resistance moving as these drop, and they're going to hit without deforming in any way. That's the sort of implications we're talking about. And this was a 200 kilogram drive. So for part A, what we need to consider is we've been given an S. This is just a SUVAC question. So S is 10 meters, U is 0 meters per second, V is what we want to work out, A is to gravity, and we don't need to worry about time at all. So we're using the standard equation v squared equals u squared, and on to AS. Because of the nature that we're talking about a velocity that's falling downwards and gravity, I'm going to choose positive to be downwards. My positive values are all downwards, just from my equation. So v is what I want to work out. U was 0, add on 2 times g times the displacement. So it starts at 0, winds up at 10, so multiply by 10. So v squared equals, and if you do this calculation, 196, so v is 14 meters per second. Okay, and these are the numbers I happen to know off the top of my head. You can do them on the calculator. Second part, B, the common speed of the pile driver immediately after the impact. So this is actually the impulse and momentum part of the question. And what we're talking about is conservation of momentum. Normally you can actually get away with saying COM, conservation of momentum. You should state what you're using. So conservation of momentum is the total momentum before must equal the total momentum afterwards. Now, you don't necessarily need this M2 in there to start with, but I put it in to show clear understanding of what's happening. So M1 is 1,000 kilograms. At the start of the conservation momentum, we are now talking about the time where this is actually now travelling at that 14 meters per second. So that's just before the impact. We have the impact, and afterwards we're going to have a velocity of v1 and v2. Because we're going to make an assumption that they move together. Okay, so we're going to assume they move together. So V1 equals V2, which I'm going to call V overall. So the velocity before was my 14 meters per second. The mass of 200 is travelling at nothing. The mass of 1,000 afterwards is travelling at the velocity V, and so is the pile. And we're guessing this V is going to continue downwards, as that's the direction of the momentum. Rearrange everything and we get 14,000 equals 1,200 V, so V equals 1,400 over 1,200, 14,000 over 1,200, which gives us an acceleration somewhere in the region of a velocity as they move off of 11.6 recurring meters per second. Okay, that's what happens immediately after if they are travelling together. So now we need to find out how far this whole system moves under this resistance. So we're going to now model the part C. The whole thing is acting as one particle. They've been effectively bound together, so this is 1,200 kilograms now. It begins its journey, so this is now, for part C, we've now got a new velocity, initial velocity of 11.6 recurring meters per second. Now you could use different letters here or talk about the part of the question. I'm using the diagrams to be clear what my changes are. This is going to move downwards with a force due to weight pulling us down. So this is 1,200 G. They say there's a resistance to motion, and the resistance to motion was 120,000 newtons. Now, one of the problems people have is they'll forget that there's still weight acting. Don't forget the weight. This is still needed. We get a velocity at the end, which is 0. We want to know what the acceleration is. I'm going to assume the acceleration is going to wind up going that way. The net acceleration. So we need to create our motion, our equation of motion. So let's look at the forces acting first of all. We've got choose a direction, and we want to know how far this actually travels under this time as well. So we need both these components probably along the way. So let's look at the motion first, the forces. And we'll consider positive as being up. So the forces were moving up. We have 120,000 newtons, sorry, minus our weight, which gives me a net force of 1,200 times 9.8 minus, and that gives me a net force of 108,240 newtons. That is actually equal to my accelerator, leads to my acceleration. So the motion part MA is equal to this force. My motion is the balance of forces. So what we used to have was the motion and the forces acting. And that one was weight, and this is resistance. Sort out the acceleration, which is this number divided by the mass, 108,240 divided by 1,200, and that gives me an acceleration of 90.2 meters per second squared. Make sure I keep that number handy, make sure it's in my memory of my calculator because I need to use it accurately. So we now know what A is, we want to know S, so this is a SUVAT part of the question. S is what we want to know. U was 11.6 meters per second and going downwards. V was 0 at the end. A is equal to, and again we're going to keep positive upwards. A is now 90.2 meters per second. T we don't know. So we need to use, again, it doesn't use the T equation, so we're using the V squared equals U squared add on 2AS. Put our values in, all squared equals minus 11.6 squared plus 2 times 90.2 times the distance it's actually travelled. Rearrange all of this, and the displacement in the positive direction is going to be 116.6 squared divided by 2 times 90.2, and this will give me my displacement, and this is negative. So 11.6 all squared divided by 90.2 divided by 2 again, and that gives me minus 0.746 meters in the positive direction. Positive we said was up, so it actually goes in, drives 0.746 meters down into the dirt. The last part, they're asking you to comment on this model in relation to the motion of the pile driver immediately after impact. And it's this assumption that the two particles will immediately join together. So part D, we assumed that the pile and the driver move together immediately after impact. So same velocity. There's no bounce. Okay, and the reason they've got this, if we have a look at the actual physical one, on the top here, clear out my little squiggly bit, you can see actually there seems to be some sort of cushioning thing here on this weight, and that's so that when the weight comes down it doesn't bounce, because that's less efficient than if we can damp this maximally. So this comes in and transfers as much of the momentum straight into the pile in one go. It's trying to make the full impulse act over as long a time as possible. Okay. That's that question. And like I said, it's one of the nastiest ones I've seen involving everything.